All right. First of all, I wanted to start off by thanking everybody for coming on a Monday before the main conference starts. Really appreciate you taking the time to come here so that we could talk about what we're up to with Nemotron. Okay, so why are we building AI at NVIDIA? I get this question a lot. Sometimes people are confused. They think of NVIDIA as a chip company, and they're like, hey, NVIDIA makes awesome chips, but why do you have to make AI as well? And so what I'm going to try to do today is explain to you why we're building Nemotron, what it is, and hopefully what we're going to accomplish together as a community of researchers and engineers that's trying to advance AI together. So there's different ways of thinking about AI, so what I'm about to say may be slightly controversial to some, but NVIDIA doesn't believe that AI is a one-size-fits-all problem. We believe actually in supporting institutions, companies, labs all around the world as they figure out how to build and deploy AI for their own problems. And there's a lot of different ways that comes out. You know, these days we're seeing a move towards systems of models being deployed rather than individual models. We're seeing a move towards specialized AI. You know, AI is always a function of the data that goes into it. Data is absolutely crucial to AI, and it's also the case that the world's most valuable data is its most sensitive data. And so the most impactful applications of AI are going to be working with sensitive data, and that means that they need to be deployed safely. Every company that has sensitive data is already dealing with how to keep it safe. And when they use AI to solve important problems, they're going to need to be able to do that in their own way as well. So we really believe in specialized AI. We also really believe in efficiency. You know, there's different perspectives on how to build AI. What is it about? At NVIDIA, we are an accelerated computing company, an AI infrastructure company. So we come to AI asking the question, how do we make it faster? And we have a strong belief that faster AI is smarter AI. Jensen recently has been talking about 3 different scaling laws. We have pre-training. Basically, the more efficient we can make the model during pre-training, the more tokens we can show it during pre-training, the smarter it can be. Post-training, the more efficient we can make the model during post-training, the more we can align it to the various kinds of problems that we want to solve and make it safer and smarter and more useful. And then finally, at inference time, when we deploy a model, the faster a model is, the more cycles it gets to think, the more problems it can solve, the more useful it is. And so we come to this maybe from a slightly different perspective. I would also say, it's important when we're talking about openness. We're going to be talking about why is Nemotron built the way it is? Why are we building it as open as we are, and trying to make it more open in the future? Is that NVIDIA is a different kind of AI company. NVIDIA is the only AI company that works with every AI company around the world, both small and large, AI native companies, old established enterprises, all over the globe. Companies work with NVIDIA. We partner with them to help them succeed. And because of that, our approach to Nemotron is very different. We're not trying to make a model that NVIDIA controls. What we're trying to do is support the industry. We're trying to make it possible for engineers and researchers around the world, embedded in companies around the world and labs around the world, to make AI that solves problems in new ways, because it's in our interest, because we know that if we can help AI grow, that's an opportunity for NVIDIA to grow as well. So that's important. I think whenever we're talking about openness, it's important for people to understand what are our incentives, why are we doing it, so that you can gauge the strength of our commitment to openly developed AI. Now, Nemotron is what we call all of our AI efforts at NVIDIA. It is models, so we make 3 different sizes of models. We call them Nano, Super, and Ultra. You can think of Nano as designed to be deployed on one relatively small GPU. Super is maybe to fit on one node of what our most recent system is, and then Ultra is going to be, we want to have the absolute largest, most amazing model that we know how to build. But the models, and we provide the weights openly. The models, I think, are less important. Really, they're the outcome of all of the work that goes into Nemotron. The data, we release our data sets, our pre-training data sets, our post-training data set. We release our libraries, so the software that goes into making Nemotron, we provide that on GitHub and on Hugging Face. And then, of course, there's a lot of research efforts that go into Nemotron from researchers around NVIDIA. All of these things come together to form Nemotron. So when you hear us talking about Nemotron, in our mind, it's not just a model. And I know that's different from the way that other organizations may talk about the work that they're doing. But again, that's because NVIDIA is a different kind of company trying to do a different thing. So Nemotron has two jobs. The first job is really inward focused and really critical for our own work, which is that we're trying to develop AI infrastructure for the future. And if you think about it, in order to do that, you have to deeply understand what AI is in order to accelerate it. And I'll be talking about that in some more detail throughout this talk. But suffice it to say that this is a core part of NVIDIA's work when we're thinking about, for example, what Rubin or what Feynman system architectures look like. How does networking work? What kind of numerics and sparsity acceleration goes into these products? How does the CPU connect to the GPU? And all, how does multi-node NVLink work? All these things. The answers to those questions depend critically on the kinds of AI that we're thinking about, right? And so we have to, in order to build systems that help the community develop new AI, we have to know what AI is. So that's a core part of Nemotron's work. The second part is, which is probably more interesting and more important to you and to the NeurIPS community generally, is that we're trying to accelerate the ecosystem. One of the things that we're most proud about at NVIDIA is that every day researchers and engineers around the world invent new things by working with NVIDIA systems that have never been built before. There's so many examples of this, but just think about the AlexNet model that kicked off the deep learning revolution back in 2012, done by a couple of grad students in Toronto. Of course, they were amazing grad students, right? Alex and Ilya, and under the supervision of Jeff Hinton, they did amazing things. But, they thought about what would it be like to train a new kind of neural network that was a lot bigger, trained on a lot more data. What could we do with that? And in the process, they built an image classification network the world had never seen and kicked off, a revolution. We love it when researchers are able to do that. And we want to support that. We want to accelerate that. And so that's the second job for Nemotron. We really feel that in order to do that going forward, the world needs a vibrant, openly developed community, openly developed AI that the community can work with and extend and invent from, using that as a basis for the future. So a couple of principles that go into building Nemotron. Why are we building it the way we do? First one I already talked about. We think that faster models are smarter models. The second one, what does that mean? Well, we're trying to develop it for production systems to run fully loaded. That's another way of thinking about that, is that we're trying to, make it absolutely as cost effective as possible. It's always the case that there's a trade-off between user experience and cost. The very best user experiences are going to be the most expensive ones. The very cheapest user experiences are probably going to be the worst ones. So we want to think about that. We want to make sure that the models we're building are designed to keep the production systems fully loaded, so that they're kind of trading those two things off and giving a good balance, giving a really good user experience and at a really affordable cost, so that it can be deployed broadly. And then the third thing is that we're designing it with particular accelerated systems in mind. So I said earlier that Nemotron models come in three sizes: Nano, Super, and Ultra. You can see in this picture, we've got like Nano, like a little DGX Spark. We've got kind of a medium-sized computer. We've got a huge computer. When we're designing each of our models, we have to make a lot of decisions about what is the model built, how many layers does it have, what's the size of the layers, what's the size of the various embeddings, and how do we think about mixture of experts and so forth, and we're informing all of those by the hardware that we're targeting. So it's specifically designed for particular systems. We think that the co-design of the model and the architecture is going to be really important for making AI faster and therefore smarter. Okay, so just a little bit of philosophy here. NVIDIA started out with an observation 32 years ago, actually, that the way that you bring a technology to market really has a huge impact on how it's received. We often call this the difference between parallel and accelerated computing. The GPU is an extremely parallel computer, right? But all of the parallel computing startups of the past, they've all faded away. Cray supercomputing, MassPar, the connection machine. There's been a lot of attempts to build extremely parallel computers over the past 50 years, and they've all failed. And the reason really is because replacing the entire ecosystem of software and hardware is almost impossible. Now, accelerated computing is basically the same technology, right? Our GPU is a very parallel computer, but it's a different framing. Accelerated computing is about plugging something in rather than replacing. It's about adding something for a specific purpose. It doesn't have to do everything. So I asked ChatGPT to draw us a picture of somebody sticking a GPU into a computer. So it's like we have this GPU, we're going to plug it in, and then we're going to make every computer better because we plugged in this GPU. So when we're thinking about the development of AI and the openly developed AI ecosystem that we want to build, this is the analogy that's in our mind. We want to build a thing that can plug in to everybody's AI and make it better, just a little bit. It's not designed to replace all AI. So Nemotron is not, again, it's not about the model. We're very proud of our models, and we hope that people use them and make great things out of them. But we actually are really happy when people build off of our models, when they extend them, when they make models that are better than our model because they were using some of the pieces that we've plugged in, or that they've plugged into their own work. Our very first Nemotron model was actually done in conjunction with Microsoft. So we have a history of collaboration. Back then, we were trying to show Microsoft that it was possible to train really awesome LLMs on big GPU systems, and that collaboration went really well. We've worked with a lot of other companies as well. We've worked with Mistral. We love working with Mistral. We love seeing the awesome models that Mistral is putting out there. We've released some models together with Mistral. We've also worked a lot with Meta's models. Llama has been a really important part of the ecosystem, which we've been really glad to support. And also build models, using Llama technology, right? So Llama Nemotron, we were, able to add NVIDIA reasoning technology to Llama, and our Llama Nemotron reasoning models have been, pretty well received, and we were really happy about that, right? So we were happy about working with them. We're happy to work with everybody, and again, we're providing Nemotron to support the industry, not to try to make everybody use all of our things all the time. We're just trying to help the industry grow. Here's some examples of open source projects that NVIDIA has been involved with in sort of the more modern AI era, starting in 2019 with StyleGAN. That's also the year that Megatron LM was released. Megatron LM is our software for, is a research project, a systems project about how do we train large transformers on NVIDIA systems. And we're continuing to develop it to this day. Since then, there's been a bunch of other projects, including some of the ones that I've already talked about, our Llama Nemotron models, our Mistral Nemotron models, our VLM models, which were really great VLMs. So we continue to contribute, and we've been recognized recently for the breadth and the strength of our contributions to openly developed AI. I hope that continues. I expect it will. One thing I was really excited about is this new Artificial Analysis Openness Index, which I believe was just released today. Is that right? Just today. We have some of the team that worked on that with us, and they're actually going to have an event tomorrow, I believe, at 1 p.m., which I would recommend you go to if you're interested in this topic. But basically thinking about like how do we rate openness in different dimensions for different efforts around the industry. How open is the model for availability? How transparent is the methodology? How transparent is the data for pre-training and post-training? And we were really proud that our Nemotron Nano V2 model scored fairly highly. Up there, not quite as good as Ulmo 2. We're really glad. Also, see Ulmo 3 came out this week or last week. Great work from the Allen Institute. We're really proud of the openness that we've been able to develop Nemotron into, and we expect it's going to continue to grow more open over time. So, okay, let's talk a little bit about the models themselves and what we're excited about. The most recent model that we released is called NVIDIA Nemotron Nano V2. It is a commercially deployable hybrid SSM with a fairly friendly license, we think. 8% of the layers are full attention, and about 45% of the layers are Mamba 2 SSM layers. Why did we build Nemotron Nano V2 out of hybrid transformer and Mamba 2? It's because we found it provides a better trade-off in terms of intelligence and inference cost. And as I said earlier, we're trying to make Nemotron the fastest model because we believe the fastest models are the smartest. Because the Mamba state in an SSM model is not proportional to the sequence length, that actually means that we can fit bigger batches in the same memory on the GPU, and that helps with utilization, makes the GPU more efficient. But it's also more accurate than traditional transformers in the studies that we've done. We did extensive studies. We published a few tech reports about that are on archive if you want to take a look at the data. But we've been really excited about that. Now, one way of thinking about faster models being smarter is just to give a model a different amount of time to think and then see what it does. We did some experiments with Nano V2 9B versus QN 8B, and you can see on the x-axis this is a logarithmic chart, so every increment is doubling the amount of time that we get for thinking. And you can see that on these different benchmarks, the nano model is just always getting a higher quality result for the same amount of thinking time. And that's under the assumption, again, that the models are fully loaded, right? That the data center is fully loaded. That's how we get to these numbers. We see the speed up significantly better at long context use cases and at high concurrency. And of course, we've released FP4 checkpoints to take advantage of Blackwell. I wanted to talk about our VLM capabilities for a bit. These days, language models do a lot more than just language. They also need to understand images and video and audio and produce images and video. So we have these different encoders that can take different kinds of data and stick them into tokens and then stick them into the LLM. That allows the model to understand some things about the scene. You can ask it questions. It can do in-context learning. It can do some zero-shot generalization and complex reasoning, and also use chain-of-thought thinking in order to solve questions that refer to images. So obviously, these kinds of capabilities we think are important. About a month ago, we released our visual language model version of Nano V2, and we were really happy to see that the accuracy went up over a lot of different benchmarks that we cared about on compared with our prior vision language model. Along with that, we have a special Nemotron model called Nemotron Parse, which is really a specialized VLM for document extraction. We find that a lot of customers, a lot of people trying to solve real-world problems with AI just have piles of PDFs that are hard to deal with. And they want to convert those PDFs into a form that can go into a database so they can ask questions of it. And so we built a special Nemotron model just for that called Nemotron Parse, and we're Really proud of its accuracy for table extraction. Again, it's something that our customers asked for a lot. And it outputs basically structured documents from image input. So that's also been a key part of us building the data sets that we use for Nemotron internally. So when we release our pre-training and post-training data sets for Nemotron, there's a lot of virtuous cycle happening here where we're able to use better LLMs to extract higher quality data to train smarter AI. So our next one, which is going to come out soon, it is not out yet, but I hope it'll be out in the next couple weeks, is NVIDIA Nemotron Nano V3. This is basically an evolution of our prior V2 architecture, just adding MOE capability. So it is still a hybrid Mamba SSM, but it also uses MOE layers. And it's a 30 billion total parameter model with 3.5 billion active parameters. We find it to be comparable or better than QN3 30B, as well as our prior Nano model. But we also see some compelling speed benefits. So, at a thinking setting of 128 input tokens, 32K output tokens, so that's a lot of thinking. We're seeing that we're 6 times faster than QN3 30B and 1.5 times faster than GPT OSS 20B. So we're really excited about that, and some of the talks today are going to be going into more detail about this upcoming model. We're also currently doing post-training for this model. Our internal checkpoint right now, when we estimate, this is an unofficial artificial analysis index score, when we estimate that, we're getting about 50.6 for Nano V3 as of a couple weeks ago. And again, that's comparing to 52 for GPT OSS 20B high. But this is a faster model, right? And so we're really proud of those capabilities. Another thing that we're really proud of with our Nano V3 is our budget control. We've put a lot of effort into training the model so that it can be interrupted. So you can basically have the inference procedure decide how much time and how many tokens it should get to answer a question. We think that's something that people really need. All right, so talking about beyond the model, what else are we releasing? We've released a lot of data sets. So we've released our pre-training data set. Our most recent version of that is called Nemotron CC V2, which is common crawl snapshots through 2025. We've done a lot of deduplication and synthetic rephrasing using QN3. It also has a lot of question-answer pairs translated into 15 languages to support multilingual reasoning. We have a math-focused data set, which we derive from Common Crawl. I'm going to go into that in a little bit more detail in just a second. We also have a code data set, which is a large-scale code data set that we sourced from GitHub and filtered with a lot of work with deep duplication, license enforcement, quality checks, and also contains some QA pairs. And then an SFT data set specifically for STEM, academic questions, reasoning, and multilingual domains. So that's, we found that these data sets that we're releasing have been really important to the development of Nemotron, so we hope they might be important to other people as well. So talking about the math data set, I thought this one was particularly interesting. If you think about math on the internet, it's a very non-standard kind of thing. There's a lot of different ways of representing math. It could be an image, it could be LaTeX, it could be some sort of JavaScript library. When you try to extract math tokens from Common Crawl, you'll find out that it's actually quite difficult to do because of the diversity of representation. And so we thought, well, how about we use an LLM to do that? So we used Lynx, which is a text-based web browser that can actually deal with a lot of this, to render math. And then we use LLMs to extract the text from Lynx and then turn those into tokens that we can use to train our model. And that has actually significantly boosted our accuracies in the math domain. And again, this is all on Hugging Face. Okay. I wanted to talk briefly also about cuTile. So stepping away from data sets and models and going into GPU computing, something I think important is happening in the way that people program GPUs, and this matters a lot to innovation in AI. So for any of you that are trying to invent the next kind of AI model that's maybe a little different, hopefully a little smarter than the standard ones that we know and love, you may need a tool like this. And the idea is basically, rather than writing your code in a traditional CUDA style where you have a bunch of threads that you map the threads onto your data, the idea is that you write a model that works on tiles, and you have the compiler figure out actually how to schedule all the data movement and the computation on the GPU for you. And you do that in Python. So it's a higher level way of programming, it allows the compiler to do a lot of things for you that the standard CUDA compiler couldn't do. And then that makes it possible to iterate more quickly on ideas of how a new neural network should be built. There's a lot of work that we're doing in our compiler team to take this tile-based model and map it onto the GPU. And so if you're able to think about some new kind of layer that you're thinking about in a tile-based way and write it that way, we are pretty excited about going forward how that's going to be able to take advantage of future hardware that we build for AI. So it's more portable. I think that the challenge, we've been evolving the GPU very quickly in order to specialize it for AI. The challenge is, how do you then make it fast enough on new things as the GPU continues to evolve. So we think these array-based models are going to be better for that. And so I wanted to highlight that today. Okay, so I'm going to wrap up now. Sort of with an observation, like what is accelerated computing? What's the business that NVIDIA is in? Actually, accelerated computing slows most everything down. Why would I say that? Well, it turns out like nobody wakes up in the morning and says, I would like a slow computer. Could somebody please figure out how to make a slow computer? Like the idea that computers should be fast, that's not new. That's not interesting. It's not unique to NVIDIA, right? So what is accelerated computing? Well, it's actually about focus, right? Actually, the vast majority of compute, we're just not going to care about. We're going to let a standard general purpose system handle that, and we're going to focus on the things that really matter. That's how you are able to get transformational speed ups, right? Is by focusing on the things that matter. But it asks the question, what is it that you're going to accelerate? How do you know that that's what you're going to focus on? And if you make the wrong choice and you accelerate the wrong thing, thereby decelerating the right thing, you're going to be in trouble. So you have to think about the problem from the first principles. And beyond the GPU these days, acceleration is coming from interconnects like NVL72, our 72-way NVLink that allows 72 GPUs to read and write each other's memory at a really high speed. It comes from numerics and sparsity. These days we're pre-training our models using FP4 arithmetic. That is a brave thing to do, using 4-bit arithmetic to pre-train a model. That's a brave thing to do. We're doing it because we know that it's more energy efficient, because we know that it's going to provide acceleration on future systems. And we know that, again, more efficient AI is smarter AI. Acceleration comes from neural net architectures, so I've been talking about hybrid SSMs, I've been talking about MOEs. These things have a huge implication on the speed of a network when it's being trained, when it's being post-trained, when it's being deployed. Training data sets is part of accelerated computing these days. Our Nemotron V2 data set actually accelerates pre-training by a factor of 4 over our prior version of our pre-training data set. And what do I mean by that? Well, if you just look at how much time you're putting into pre-training and how accurate your model gets during pre-training, our models are learning 4 times faster. There's 4 times more intelligence per token in this data set. And that took a year for us to develop and about 1 million GPU hours, so a not trivial amount of work went into that. But if you think about it, that's actually a faster rate of increase than you could get from any chip, right? By making your data set smarter, you've accelerated pre-training. So data sets are part of accelerated computing. Optimizers are part of accelerated computing. You know, what optimizer algorithms are we using have a dramatic impact on how quickly a model learns. And these days, the brevity of LLM response, also a critical part of acceleration, right? If we think about test time compute, you know, how many cycles does a model get in order to think when a model's deployed? If your model is very verbose and just keeps talking and talking but doesn't actually think and doesn't get anything done, then it doesn't really matter how many microseconds of compute per token you get to apply if the model takes 10 times more tokens to come to the answer. So that means actually that application level concerns like how quickly can a model decide an answer is now a critical part of what it means to accelerate AI. And that's the reason why you know, we are going to continue doing Nemotron forever, and why we hope to make Nemotron something that's really useful to all of you. We hope that all of this work into accelerated computing is going to continue helping the community build the smartest and best AI, hopefully with new ideas that none of us have ever even thought of before, that some of you are going to invent. And so that's the idea behind Nemotron. Nemotron's more than models. It's all of our work in AI, our research, our data, our libraries, and yes, our models too. It's essential to our strategy. We're going to keep doing this because it's necessary for our main work, and also because we know that when we empower the ecosystem, it's an opportunity for NVIDIA, and we want to make sure that we maximize that. So with that, I'm going to wrap up, and then we're going to transition into some more focused talks about specific aspects of the Nemotron work. So thank you.